All right. Hello, everybody. I'm going to go ahead and go through these three examples for related rates day 2, just because I know we have a lot of people gone for state volleyball. So it seems just like the easiest way to do it. So I'm going to start with this first example. This is kind of a continuation of what we had started last week. It says a fish is reeled in at a rate of 2 feet per second from a bridge 16 feet above the water. At what rate is the angle between the line and the water changing when there are 20 feet of line out? So if you recall from last week, we want to start with our given information. And we are given that a fish is reeled in at a rate of 2 feet per second. And so we need to somehow come up with a way to represent this. If you're dealing with a fish in the water, you've actually got a triangle. So you need to determine that that's your shape. So you're standing here and you're reeling a fish in down here. So your fish is here. This is your water. And then this is the line. Excuse me. And it says you are standing on a bridge 16 feet above the water. So we can actually fill in this 16 feet here because that's not changing. You're not jumping in the water to go get the fish. So you're going to be at 16 feet forever. So that's that. We are looking for at what rate is the angle between the line and the water changing. So that's what we're eventually looking for here. So we are actually given that a fish is being reeled in at a rate of 2 feet per second. So this line right here is decreasing at 2 feet per second. I'm going to call this dH dt, H for hypotenuse in this triangle. That just seems like the easiest way to do it. And we know that's negative 2 feet per second. And we're supposed to find the angle, which we're going to call d theta dt, when the water change or the water level, when there are 20 feet of line out, sorry. So when my H or my line is 20 feet. So that's that. So we have what we're given, what we're trying to find. We just got to figure out how to set this up. And so the best thing to look at here is we're involving H, and then we're involving another variable, but we don't necessarily know specifically what variable. So we got to kind of think about that. So if you're looking for dH dt, we know we have to use this one. And then the only other one that we know is the 16 feet. That's our constant rate. And so you're going to want to choose a trig function that involves the 16 and your hypotenuse because those are the two that you're dealing with. And that would be the opposite and hypotenuse, which is sine. So I know sine of theta is equal to the opposite side, which is 16 over h. And recall, if we're trying to derive this, it's easier if we write this as sine of theta equals 16h to the negative 1, because then finding the derivative is a little bit simpler. So once you have your function written, then we're going to implicitly derive it. So the derivative of sine of theta is cosine of theta. Don't forget the d theta dt. And that's equal to, power rule here, negative 16h to the negative 2. And that is dH dt. You can rewrite that if you want to as cosine theta d theta dt equals negative 16 over h squared dH dt. And then from there, it's just a matter of plugging in the stuff that you know. And so because you know this is 16, you're looking for cosine of theta. And cosine, remember, is adjacent over hypotenuse. So you need this length here of how far away the fish is from the bridge. And it tells you something about some other parts of the triangle that'll help you get there. And if you look at the beginning information, it says, at what rate is the angle between the line and the water changing when there are 20 feet of line out? So this is when you can actually put your 20 there because you've already derived it. You don't want to plug in those numbers that are changing until you're ready, until you have the derivative. So if I know that's 20 and that's 16, I don't know if you remember this from geometry, but this is considered a Pythagorean triple. And a Pythagorean triple gives you ratios of side lengths of common triangles. And this is actually a 3, 4, 5 triangle. And so it's a ratio of a 3, 4, 5 triangle. So that's 20. That's actually the 5. The 4 would be the 16. And then this would be your 3. And so in order to get 16 and 20, you had to take these both these numbers by 4. So this one's going to have to be 3 times 4, which actually gives you 12. And so that will give you the information you need to find cosine of theta. And so I can replace cosine of theta with adjacent over hypotenuse, or 12 over 20, d theta dt. And then I can set that equal to negative 16. My h, we know, is 20. And dh dt is negative 2. And then it's just a matter of simplifying this from here. So 12 over 20 can be simplified if I divide both by 4. That gives me 3/5. And so I'm going to make the numbers a little bit smaller because I don't get a calculator. So 3/5 d theta dt is equal to, let's see, negative 16 times negative 2 is 32. And 20 times 2 is 400. So we've got that. And then in order to solve for d theta dt, we want to multiply both sides by 5/3 in order to get rid of that fraction. So we're going to get rid of that. And then I have d theta dt equals 32 times 5 over 400 times 3, which I'm going to try to simplify a little bit here. Let's see. I can cross off this. So 5 divided by 5 is 1. 400 divided by 5 is 80. So I've got that. And then I can probably simplify a little bit more with the 32 and the 80 if I want to. So I can divide these both by 8. So if I divide 32 by 8, I'm left with 4. If I divide 80 by 8, I'm left with 10. So right now I have 4/10 times 1/3, which becomes 4 over 30, or 2 over 15. So d theta dt is equal to 2/15. Since we're dealing with an angle, this is actually radians per my time, which my time was seconds. So the hard part there was just simplifying the fraction, but that is how you do a problem involving a change in an angle. I'm going to pause this and let you think about that, look at this over a little bit, and then I'll make another video for the other 2 examples.